Example 2.1, 3 charges. Figure 2.9 shows 3 fixed point charges. Q1 equals plus 1.5 microcoulomb, Q2 equals plus 2.5 microcoulomb, and Q3 equals minus 3.5 microcoulomb. Charge Q1 is located at 0A, Q2 is located at 0, Q3 is located at B0, and where A equals 8 meters and B equals 6 meters. What electric field E do these 3 charges produce at point P, which has coordinate BA? Okay, so we have 3 charges, Q1, Q2 and Q3. Q2 is at origin, Q2 is placed at the origin, Q1 is 8 meters away from Q2 on positive y-axis, Q3 is 6 meters away from Q2 on positive x-axis. Yeah, so we have a point here which has coordinate BA. Point P has coordinate BA. BA. That means point P is B units on x-axis and A units on y-axis. B is 6 meters and A is 8 meters. Right. So this is point B. Point P. Yeah. So we have 3 charges. Each charge will produce its own electric field. So we are going to find the net electric field at point P due to all these charges. Okay. Yeah. So net electric field at point P is equal to electric field produced by charge 1 at point P plus electric field produced by charge 2 at point P plus electric field produced by charge 3 at point P. Yeah, right. So all these are vectors, right? Yeah, because it's a two-dimensional problem, we have to treat them as vectors. Okay, so the equation for electric field, this is the general equation for electric field due to a point charge, K Q over R square. That's the equation, K Q over R square. Okay, so using this equation, we are going to find the electric field of all these individual charges, Q1, Q2 and Q3. Okay, let's start. Let's start by finding the electric field by charge 1, Q1 at point P. Yeah, so the equation is KQ by R square. Yeah, K is K, Q is Q1 divided by distance. Distance from the charge to the point where you are measuring the electric field, right? So this distance, this distance. Okay, what is that distance? That distance is 6 meters. B 6 meters, right? Yeah, so sorry. Yeah, 6 meters. 6 meters. Right. It's same as B, right? B. This side is same as A. A equals 8 meters. Okay. So B square. Distance between Q1 and point P is B, which is 6 meters. K is Coulomb's constant, 9 times 10 to the power of 9. Q1 is 1.5 microcoulomb. 1.5 microcoulomb, micro is 10 to the power minus 6 coulombs, yeah, divided by distance B, B is 6, so 6 square. If you do that in the calculator, you will get 375. It's electric field, right? So Newton per coulomb, right? Okay, so let's find E 2 electric field by charge 2 at point P. Equation is K Q2 over, yeah, we're talking about charge Q, right? So Q2, K Q2 divided by, okay, what's the distance between charge Q2 and point P? So this is that distance, right? This is that distance, right? How do we find that distance? It's very simple. We can use Pythagorean theorem. Okay, I'll connect these 2 points. Yeah. Yeah. Just give me a second. Okay. This is the distance, right? How do you find this distance? Let's use Pythagorean theorem. It's a right angle triangle. So this distance will be square root of 8 square plus 6 square. 8 square is 64. 6 square is 36. So root of 100, which is 10 meters. So this side is 10 meters. Yes. Right. So square root of a square plus b square. Yeah. Substitute the values. K is 9 times 10 to the power of 9 times Q2. What is Q2? Q2 is 2.5 times 10 to the power minus 6. 2.5 times 10 to the power minus 6 over root of a square plus b square, that is 10 meters, right? So 10 square. Let's solve it in the calculator. So you will get 225 Newton per coulomb. 225 Newton per coulomb. That is electric field by charge 2 at point P. Now the next one, the last one, E electric field by charge 3 at point P. The equation will be KQ3 by, okay, what's the distance between Q3 and P? A, right? A, which is 8 meters. So A square. Okay, substitute the values. 9 times 10 to the power of 9. Q3 is minus 3.5, but we are finding the magnitude, so I ignore the sign for now. Yeah, we'll consider direction later, so ignore the sign. 3.5 microcoulomb. So 3.5 micro is 10 to the power minus 6 divided by A is 8, which is equal to 8 square. Yeah, so if you solve it, you'll get 492.19 Newton per coulomb. Let's find the direction of these electric fields. Okay, so let's recall the direction of electric fields. Let's say we have a positive charge. The electric field produced by this point charge will be going away from it. This is the direction of electric field vector, radially outwards, just like this. Okay, that's for a positive charge. Now if you have a negative charge, the electric field will be coming towards, the direction of electric field will be towards the charge, towards the negative charge, just like this. Yeah. All right. So using this idea, we are going to find the direction of electric fields at point P. Okay, Q1 is positive, is a positive charge. So electric field produced by Q1 will be like color. Yeah, be like this, right? So what will be the direction of electric field at point P? It's easy, just draw a straight line connecting these 2 points. Yeah. Yes. Okay, so that is the direction of electric field at point P. This is the direction of electric field at point P. So this is electric field due to charge, electric field by charge 1 at point P. Now what about Q2? Q2, the electric field produced by Q2, the direction will be just like this. Okay, this is the direction. So this is electric field produced by charge number 2 at point P. The direction. Okay, now what about Q3? Q3 is a negative charge, right? So the electric field vector should be pointing towards the charge. So electric field vector should be pointing towards the charge, just like this. Just like this. Yeah. It will be towards the charge. So this is electric field by charge 3 at point P. The direction of electric field at by charge 3 at point P. Okay. So we have to resolve these vectors. Then add x components and y components together to find the net electric field at point P. Okay, let's draw a table. We will treat x and y components separately. So let's draw a table. All right. So we have E1 to P, E2 to P, 2 at P, electric field by charge Q2 at point P, E3 at P, 3 at point P, and finally we will find the net electric field at point P by adding all these components together. Yes. So this is x component here, this is y component here. Okay. So E1 to P, E1 to P. I'll draw this vector separately. E1 to P. E1 to P is pointing towards right on positive x-axis, right? This is E1 to P. Yeah, because this electric field vector is on x-axis, is on positive x-axis, it has no y component. So E1 to P is same as E1 to P x component. Okay, there is no change. There is no, because there is no y component, the whole vector is just the x component. Okay, so E1 to P is equal to E1 to Px. So what will be the x component? Same as E1 to P. E1 to P is 375. So that's our that's our x component of vector E1 to P. What about y component? Is there any y component? No, there is no y component. It's 0. Yeah. Okay. So we got the first one. All right. All right. Now what about E3 to P? The third one. Right. The third one. E3 at P. Electric field by charge 3 at point P. Yeah, so I'll draw the vector here. This is that vector. It is on negative y-axis, right? So this is E, 3 electric field by charge 3 at point P. Yeah, this is pointing vertically downwards on negative y-axis. Yeah, so there is no x component for this one, only y component, right? So this is equal to E3 to P y component. Yeah, there is, because there is no x component for this vector. It's on negative y-axis. All right. So what is what is E3 to P? It's 492.19. So 492.19. Is there any x component for that vector? No, there is no x component, just the y component. So this is 0. All right. Now let's find. Let's resolve E2 at P. Electric field by charge 2 at point P. All right, so I'll draw that vector. This is that vector, right? E2 at P. I'll draw that vector. Okay, so this is that vector. This is point P. This is point P. This is that vector. Now, how do you draw the components? It's easy. This is the x component, right, on positive x-axis. This is E2 at P. So this will be E2 at P, x component. How do you draw the y component? This is the y component, right? E2 to P y. Okay, so these are the components. To find x component and y component, we need an angle, right? Either this one or this one. Okay, how do we find the angle? So I'm going to complete this picture. We have a charge here, Q1. This distance is 8 meters, right? Sorry, 6 meters. This distance is 6 meters. We have another charge here, which is Q2. This distance is 8 meters. And the distance between Q2 and point P, we found that using Pythagorean theorem, that is 10 meters. Right? Okay, let's find this angle. Let's find this angle, theta. This angle will be equal to this angle, right? Opposite angles. So they must be equal. So this theta, you can, because we have all the three sides of this right triangle, you can use any one of the three trigonometric functions. I'm going to use sine, right? But you can also use cos or tan or whatever you want, cosec or, yeah. Okay, I'm going to use sine. Yeah. So sine theta equals opposite over hypotenuse. Okay, for this triangle, for this right triangle, this is 90-degree angle. So opposite side of 90-degree angle is hypotenuse. This is theta. Opposite of theta is opposite side. The side touching theta is adjacent side. Right? Yeah, adjacent side. All right. So sine theta will be opposite side, which is 8 over 10. So theta will be equal to sine inverse 8 over 10. So theta will be equal to sine inverse 8 over 10, 53.1 degrees. 53.13 degrees. 53.13 degrees. Yeah, that is this angle, theta, 53.13 degrees. Okay. So we have this angle 53.13 degrees. Now we can easily find x component and y components. So E2, sorry, E2 at P, electric field by charge 2 at P, x component will be, alright, check this picture, x component is touching theta, right? So it will be cosine, the vector which is E2 to P, cosine theta, right? So E2 at P is 225, so 225 cos 53.13 should be in degrees, yeah, 135 Newton per coulomb. Okay, let's find the y component now. E2 to P y equals, okay, y component is not touching this angle, right? This is the y component. It's not touching our angle. Our angle is here. It's not touching the angle. So it is E2 to P sine theta. So 225 sine 53.13. If you solve it, you'll get 180 Newton per coulomb. Okay, so the x component is 135. X component is 135. Y component is 180. 180. Yeah. There is one more thing. In E3 to P, y component is pointing downwards, right? E3 to P, y component is pointing downwards. So you should put a negative sign here, okay? Or this will be minus 492.19. Okay, now add the x components together to find the x component of the net electric field at point P. So x component will be 375 plus 135 plus 0. $510. It's 510. What about y component? 180 plus minus 492.19 plus 0 minus 312.19. Yeah, that's it. We got our answer. Yeah, so this is the x component and this is the y component of our net electric field vector. Yeah, so how do you write this vector? How do you write this vector? Yeah, 510. Okay, right here. Okay, sorry. Net electric field at point P, it's a vector. How do you write that vector? 510, that's the x component, so multiplied by the unit vector on x-axis, which is x cap, plus minus 312.19, which is minus 312.19 y cap. Okay, so this is our vector. That's our vector. Alright, now using this vector we can find the magnitude and direction. Alright, so to find magnitude of this vector, net electric field at point P, we can use Pythagorean theorem. 510 square plus minus 312.19 the whole square. If you do that, you'll get 597.8 Newton per coulomb. So that is the magnitude of the total electric field at point P. Now we have to find the direction, right? Yeah, one of the vectors is pointing in this direction, the other vector is pointing in this direction, the other one is pointing in this direction, right? So we have to find the direction of net electric field. We just found the magnitude. So let's say the direction is alpha. Alpha equals tan inverse E net force y component over x component, y over x, y component over x component. What is y component? Y component is minus 312.19, right? So minus 312.19 divided by what is x component? 510. 510. If you do that, you'll get minus 31.5 degrees. That means our vector, the net electric field vector, is 31.5 degrees below positive x-axis. Just like this, yeah. Oh, it's not working. Yeah. Yes. All right. So this angle is 31.5 degrees. Yeah, it's negative, so it's pointing downwards below the negative, below the positive x-axis. So that's our final answer. Net electric field is 597.8 Newton per Coulomb. The direction is 31.5 degrees below the positive x-axis.